My name is Braden McCorkle. I'm the Desai Solutions go-to for the Altair product line. I want to thank you all for sharing some of your time today. We're proud to more formally announce our partnership with Altair by introducing their casting simulation tool to you. Most of you know of our involvement with the SolidWorks portfolio, but we believe in helping our customers achieve success in many aspects of their business. This is where our partnership with Altair became important to fill other areas of business, engineering, manufacturing needs, and further complement our portfolio of solutions that we can offer to you. We hope this webinar provides some insight into casting simulation options and some valuable takeaways and exposure to this new partnership. I'm now going to pass it off to Martin Solina. He's a product manager for Altair's Inspire platform. He's passionate about helping engineers solve difficult manufacturing problems with easy-to-use manufacturing simulation tools. Martin, over to you.
Okay, thank you very much and welcome everyone. So I will present Inspire Cast. It's a simulation software for casting process. But with a new concept, we are trying to help designers and also manufacturing people to get better parts, to design better parts, and to design also better process to produce these parts. And let me introduce something that is probably our core if when you compare Inspire Cast with other softwares from in the market. Okay, Inspire Cast works in an environment that we call the Inspire platform, that is not only offering one package for casting, but is offering different tools that will help designers not only to start designing as traditionally they were doing in the past, creating shapes based on experience, but they can also use other tools like motion analysis, for example, to get the loads applied to the particular component we are trying to design. So in this case, I will use this example, okay, to go through a user case in which we will try to redesign these two brackets, okay? So for that, I create this assembly that is a rear suspension for a motorbike, okay, in which I can simulate the displacement of the rear wheel, and based on that movement, I am getting from the application from Inspire Motion all the loads that are being applied on my component. Okay, so if I want to design or redesign this component, the first thing I need to get is the loads. The second thing is to, in case of we are designing a new component, I need to create a kind of design space, okay, in which we can put or remove material. So I'm informing the software where can I put or remove some materials. And of course, I need to define some constraints to the problem. We will use a topology optimization analysis, okay, and we will create some shapes based on the material, loads, and manufacturing constraints. In this case, I'm setting some constraints for 3D printing. So the part we are getting from the topology optimization is a 3D printed part, okay, which we will use minimum support, etc., and we can simulate the 3D printing process. But also, we can, for example, the other part, we will use a casting process to produce this part. So in this case, what we will do is to create the design space, okay, and we will assign some manufacturing constraints to the process, optimization process for the casting manufacturing process, okay. So this is the first concept design that the application will generate or that the designer will create. And the question is, can we safely cast this part, okay? And to answer this question, we will introduce Inspire Cast. So basically, to design, Inspire Cast is not only a casting simulation process tool, is a simulation driven design tool to go from the very early stage of the design to the manufacturing process design. And this is what I will present and show to you in a live demo, Okay, so I will make a live demo using this particular part, and we will go from the very beginning, from the first initial design of the part, and we will try to define the whole process using simulation results. Okay, so let me go there. I will, sorry, I didn't, this is the latest. So the idea is this, going from the early design, okay, so the early stage of the design until the end of the process design, going through all the stages. So let me go and launch InspireCast, okay, and open the geometry. So InspireCast is a very simple interface, but it's a very complex software. But everything happened on background. We know the process we are trying to run. We know the conditions of this process because the user will inform us which kind of process he is trying to run, what kind of parameters we can define. So everything will be done step by step in a very easy to use manner. So let's start defining, for example, the part. Okay, we will simulate is here. So the first thing we need to do is to define the material we will use for this part. So let's say we are using an aluminum. Let's use this one by default, and the initial temperature, let's put 780 degrees. Okay, and now we have defined the part with its own material, and the next thing we need to do is to define the gate position. Okay, so for the gate we will select the gate tool. Okay, and we can create gates by clicking on the geometry. Okay, this will create a circular gate that we can change and modify to a square shaped gate. Okay, we can modify the diameter of the gate. Let's say we will use a 5mm diameter, and we can of course change the direction, okay, and the position of the gate. So we can probably move it in order to define the direction that the material takes before reaching the part. Okay, so basically we have set up the first, the lowest amount of or the minimum amount of information we need to run a simulation. We have the material and we have the gating point. Let me create the mold. Okay, by clicking on this button, we can create a basic shape outside the part that will represent the mold. We can assign the material to this mold. It can be made of steel or sand or chromite sand. We have all the materials inside the database. We can change the size of the mold by using this micro dialog. So we can say, okay, my mold is 120 by 50 by 110. So he can increase the size of the mold. Very simple. Next step is to define the basic steps, the basic setup. So in this case, I will use filling initial velocity of 0.5 meters by second. Okay, this means the velocity at the gate, so in this surface. And finally, we will define the analysis we want to run. So in this case, I will run a filling analysis and solidification. Okay, we can even, in case of permanent mold casting, we can perform cyclic analysis. We can set up the size of the mesh on the gate and on the mold, okay, based on one factor that will take in consideration the element size we are using for the part, and he will use this factor to assign element size to the mold and to the gate. So by hitting run, we will launch the analysis, okay? This simulation will take probably will take about 2 or 3 minutes, okay? In order to don't lose our time, I will open the results that I have calculated already. So, and let's see what we can see on this very simple analysis. Okay, so as I mentioned, I run a filling analysis, okay, and a thermal analysis. Okay, so let's see first the filling evolution. Okay, in this case we will see the material, how the material is filling the cavity, okay, and what is the temperature distribution, velocity, mold erosion, pressure, filling time, and cold shot. So let's start with the filling. Okay, so as you can see, the material is coming from the top, to the bottom, the gravity direction is in minus zeta orientation, okay, minus z orientation, so you can see how the material is filling the wall cavity. So another thing we can analyze is the velocities, okay, that will show us how velocities evolve in the mold. So we can take a look at turbulences we are generating due to the in-gate position. We can understand what is the highest velocity we will have inside the cavity. It is important in case we are using a sand mold to avoid sand erosion. So we can take a look at the last tears or air entrapment due to turbulences that you can see we are not in a good position, okay? There's a lot of air trapped in the part. We can evaluate mold erosion, we can evaluate pressure and filling times, for example. This will give us some information about the evolution of the material in the part, and this is not even giving us a good look and feel of the filling we are doing. We have very non-homogeneous filling time, and this is not good. So I don't need to take a look at the thermal analysis, because just watching this result of filling time and entrapments, I know that this is not a good position for the gate. So what can we do when we realize that this is not a good design? Well, we can go back, okay? We can remove the gate. We can change the orientation of the part. So by selecting gravity, I will select this surface and I will position the part in this orientation, and I will add a gate in a different location, for example, here. Okay, I will change the size, use a smaller size, okay, and I will run a new calculation. So as you can see, to run a different iteration, okay, using the same material, the same conditions, and the same setup, but changing one or two parameters like the gate position and the gate size and the gate orientation, is extremely simple. In most of the other applications, the way the path, or what we need to do is to go back to the CAD geometry, modify the gate location, size, and position, export the geometry, and start a new process. But here we can go back and forward and modify geometry and parameters alike. Okay, so let me stop this one. Let me stop this one, and I have, of course, calculated already the second iteration. Okay, and I will show you the results of the new iteration. Okay, that we have here. And we will see how the temperature has changed, the velocity and the filling time has changed. And we have now get a more homogeneous values of filling time, not too many turbulences because the gravity is pointing downwards. And we can, of course, we may have some air entrapment in this particular region, let's see, because of the evolution of the metal, but we can machine this part and remove these bubbles or these impurities we will find after production. So let me see what happened with filling time. Filling time is much more homogeneous. That will allow us to, we are avoiding turbulences and entrapments. Let's see, cold shot. We have no cold shot here regarding the gate position. We are getting a very homogeneous flow. And we can see and check the mold temperature, okay, that will be useful for during solidification. Okay, so I also run solidification in this case. So let's see what we can understand from the temperature evolution of the part and mold. So here, for example, we can put a call out, or we can put a plot. We can plot the temperature on the mold, so we can understand what is the maximum temperature that we are reaching on the mold. That is 450 degrees, more or less. Okay, we can check this in the animation, and just to avoid, in case we are using sand, we can avoid sun burning. In case we are using metal molds, we can avoid cracking problems on molds or this kind of things. So it's very, very important to have the temperature evolution in the molds, just to also, for example, for design the cooling system that we can design in InspireCast. So let's continue with the analysis. Let's go back to the temperature of the part. As I mentioned, we can visualize the evolution of the temperature. We can make dynamic sections, okay? And we can change the orientation of these sections, okay, just to see what happened in the interior of the part. We can visualize the solid fraction evolution, okay? Solid fraction is extremely important to predict porosity, okay? Solid fraction will show us, or will hide, the solidified material during the cooling process. So as you can see, the material is disappearing from the animation. In this region, that means that this material is solid. So what we can see in the screen is the isolated liquid areas, okay, that remains in the part after, for example, 3 seconds, okay. So this will give us a good idea on where the porosity will be located, because as you know, porosity came from shrinkage during solidification. So this will lead, these isolated regions will lead in porosity. But we can see, we can check porosity. So by clicking porosity, we can see that he's showing porosity in these particular locations, okay? And we can see, for example, the total porosity as a volume, okay? So here we can see that we have 20.98 cubic millimeters of porosity. Here we have 28, and here we have 12 cubic millimeters of porosity. So now the question is, how we can avoid this porosity? So basically we can place risers. In casting, to avoid porosity, the cast makers use risers. So we have tools to add. In theory, we need to go back to the CAD system, generate the CAD of the risers, and then export the geometry to the simulation software and generate the mesh. In this case, we have a tool that can create the riser for us. So in those locations that we detect that we have porosity, we can place a riser. Okay. This riser will be defined by a particular solidification modulus. We can create one riser here, and I will create one riser. I will remove the gate to put the riser just in where the gate is. This is different. This is a top riser because it's in the top surface, and this will be a side riser, okay? Because this is in a side surface. So you can see automatically he will create top risers or side risers depending on the location we are selecting for create the risers. And I can place the gate, for example, here on the riser. Okay, so now we have a new system that we have created to try to avoid the porosity. So let me load the results of this new iteration, okay, and see how the results looks like. Okay, in this case I have run only the thermal analysis because filling we don't need. We know that by filling using the horizontal position of the part is quite good. So let's see what happened only on the solidification side. So now we have the same part, the same gate position, and we have 3 risers. Okay, so let's see what happened now. So temperature evolution is normal. Let's see what happened in solidification. So as we will see, the risers will compense part of the contraction or the shrinkage due to solidification. As you can see, these risers are feeding material in the liquid, and this riser is feeding material in this region. Okay. But if we continue with the animation, as you will see, the neck of the riser, or the connection between the riser and the part, is now lost. Okay, so we cannot feed more material from this riser to this particular region. That means that all this material will be unuseful and will not compensate the solidification. Let's see what happened in these two cases. Okay, it happened in the same. So in the but some part of the porosity is not totally compensated by the risers. What can we do here? Well, basically, to compensate this and this, we can increase the size of the risers and the size of the necks. And here probably I will need to move this riser to this top position to be closer to the porosity. So let's do that. How to do that? It's very simple. We can go to riser menu, and we can, for example, increase the modulus of this riser. Okay, now it's 0.3. I will use a 0.3 here also, and I will remove this riser. Sorry, I will remove this riser, and I will create a new one, even bigger here, 0.32. Okay, to try to compensate, because this region is bigger. So, and now I have. Now let me use a 0.3 riser. I will leave it like this, 0.3. 3 risers with the same size to compensate the porosity. So I have already run this calculation. Let me open the results to show you. Okay. Okay, so now as you can see, we have the 3 risers located on the part, and let's see how it works. So let's see the porosity. As you can see, now he's showing porosity. Let me reduce. He's showing a bit of porosity here, okay, and also here. But the most of the biggest part of porosity is located in the risers now. So we are doing a great job here. Probably we can increase. Let's analyze what happened with the solid fraction. Okay. So as you can see, this now we have increased the size of the risers, and now the connection between the riser and the interior shape of the part is being alive during the wall solidification process. So this means that we are feeding material during all the time to the riser, but not here. As you can see here, we have some disconnection from the riser, between the riser and the part. So what can we do here? Well, we have 2 or 3 options. We can increase the size of the riser. That means that we will use more material to fill during the filling. Okay, so increasing the size, increasing the volume will increase the weight of the waste material we are using. It's not convenient. Or we can increase the size of the neck. Again, we are increasing the amount of material. Or we can use a sleeve. A sleeve is, as many of you may know, is a insulating component that will cover the riser and that will avoid the heat flux from the riser to the mold. So we'll keep the heat inside the riser and keep the liquid material for more time. So to do that, we can go back to the preprocessor. We can select sleeves, and we can say, okay, I want to cover this riser with a sleeve. Okay, so simple as it is, 1 click, and we can assign, for example, isothermal sleeve, 20 degrees, and with a thickness of 3 millimeters. Okay, as you can see, the size of the sleeve increased. Let me show you again, 5 millimeters. Okay, so the size increased every time I change the size of the riser. Okay, the sleeve, sorry. And now we have 2 naked risers. Let me remove. We can manually change the height of the sleeve just to make it open. Okay, we can make it open or closed, and I want to make it open just to have the cooling direction from the bottom to the top. So now we have delayed in some way the solidification of this riser. So let's see how it looks. So let's load. I'm loading the results, and let's go to the post-process side to see what is the effect of the sleeve on the solidification of the riser. So let's click on play, and again we will see the behavior of these two risers will not be affected by this sleeve. So the solid fraction will still be similar. So both of them are connected during the whole solidification process. And let's see what is changing here. So as you can see now, this riser is much more heated in this case, and the connection is still there, even long time before the solidification of the part. So this means that we can probably reduce the size of this riser. So let's see what happened with porosity. As you can see now, we have eliminated porosity from everywhere. We can see still some small amount of porosity here. Okay, let's see the volume of porosity we have there. It's very, very small. It's 2.2 cubic millimeters. That means that this hole is even smaller than 0.5 millimeters. Okay, and here we have a 3.79. This is extremely small. Okay, so as you can see, by using InspireCast, we can modify the process design. We can learn how this design we are creating works, and we can basically use the simulation to drive the process design. And not only that, many times happened that we cannot solve a problem, for example. Okay, many times happen that we cannot solve an issue here, okay, because of this hole. In many of the cases, the user needs to, as I mentioned before, go back to the CAD system, modify the geometry of the part, and redesign the part as designers, and send this back to manufacturing people. But InspireCast is totally different. So InspireCast allows us to modify not only geometry of component, but also the geometry of the part itself. So we can, what we can do is go back to geometry, for example, remove these fillets. Okay, I can ask to the application to find fillets and rounds, and I can easily remove this one, and I can easily clean this hole. Okay, sorry, clean this hole to make it to put another riser here, or to solve any particular issue. So what I want to show here is that we can modify not only the geometry of the components we are using, okay, we can also modify the geometry of the part we are designing. So designers will be able to avoid these iterations between manufacturing and design because of the part is not feasible to be produced. Let me just mention what other components we can add. We can add core systems, chillers. Chillers is a kind of component that will help us to cool the part faster. So we can change the size easily from here. Okay, and 6. So as you can see, we can add a chiller component at the bottom of the part. We can add risers, as I mentioned. We can add sleeves. We can add overflows, mold that is here, cooling lines, to add cooling lines in case of permanent mold casting is extremely simple. So we only need to select cooling tool, create a path, and he will create the cooling line for us. And we can anytime move. We can change the diameter, for example, and we can change the material and the temperature of the coolant. Okay, it's very extremely simple. We can add filters, piston shot sleeves, and Crucible for till putting cases. Okay, so based on that, we can design. We have tools to create geometry. We have tools to copy, to move, to edit the geometry. So basically, we can create the full model in InspireCast, okay, to test not only one part with the gate and with the risers, we can also test the full model with any number of cavity we want to create and with any number of components we want to assign. So in this case, I have created a very simple runner, okay, with a in-gate located here as we have defined in the initial stage, with the 3 risers placed here as we have defined in the initial stage, and with a sleeve to cover this center riser. So if I go to the post-process now, we can visualize how the material is filling the 3 cavities, okay, how the material evolves in the mold. Let me change the temperature to dynamic. Okay, we can again visualize and prove that everything works as we have planned in the initial stage. We can evaluate the solid fraction during filling, the velocity during filling, last air, mold temperature. So we can, let me move this section here. So this is section, I will orient the section in a different plane. So we can see how the mold temperature is changing during filling. Okay, once the material arrives, we can check the temperature of the mold, and we can, of course, after filling, we can check the solidification of the wall model. Okay, and we can again see how the temperature of the mold evolves and how the temperature of the part evolves. Let me turn on the part, the gate, the runner, and the sleeve. Okay, and I can place, of course, I can make some plots in my riser, in my runner, and in the part. So as you can see, we can differentiate, or we can create plots any place we want, and of course we can play plots on the mold side to evaluate the temperature of the mold. So I don't want to take more time from your side. This is a I don't know if you have questions, any requirement. I want if you have any question, you can write these questions on the poll question. So Leah, do you have any comment? Any?
Sure, it looks like we do have one question. And it is, why does the sleeve intersect the part cavity?
Okay, this is just to simplify the creation of the sleeve. Okay, we are generating a sleeve that intercept the cavity. Okay, let me turn off the mold. Let's turn on the runner. Let me open the number 5. Okay, that has only one part in the sleeve. So just to simplify the life of the user, we let the sleeve intersect the part. You can always modify the geometry of the sleeve, okay, by double clicking on this surface and push-pull this surface. But in case you generate the sleeve automatically, we internally and before mesh, we will take care of this. So if we go to post-process here, we automatically perform booleans. So you will see, if I turn off the part and turn off the riser, okay, you will see how the shape of the sleeve is intersected automatically with the cavity. So the sleeve is not penetrating, but is on top of the cavity geometry. So it's just to simplify the life of the user. But you can always double click on this surface, modify the height, and create a sleeve that is not intersecting the cavity or any other component. Any other question?
it doesn't look like we have any more at this time.
Okay. We can give some minutes to type question if they need. Meanwhile, let me talk about the future or other capabilities we have integrated. We have integrated recently a piston shot sleeve capability that allow us to simulate in high pressure die casting the piston displacement to push the material from the cavity, from the crucible to the cavity, defining the velocity of the piston. And for first phase and second phase, we have added another capability to create the crucible for tilt pouring simulation. So let's suppose we have a tilt pouring case here. I can add the crucible by clicking in this location, and basically we will rotate and tilt the part considering the material is waiting here, and when we start the tilting we will fill the material using tilt pouring process. Since we have another question, is what is the max gate velocity? So there's no max gate velocity. The idea is that the user will define the max gate velocity depending on the process. There are two ways to define velocity. In case we have the gate, we need to define, sorry, let me so we can have two situations. One situation is when we have only the gate, okay, that is representing the latest portion of the runner, okay. In this case, we need to define the velocity that we consider will get the material on the runner, okay, at the end of the runner. In high pressure die casting, for example, it's easy to set up because at the end what we are doing, we are designing the full runner to have 30 meters by second or 25 meters by second. But there's no maximum velocity. It depends on your process and in the process control you are using.